This question, we are asked which electric fan will go faster if the temperature of component X and Y increases. Okay, first of all, we have to establish the point that in order for the electric fan to go faster, the current passing through it must increase. And component X here is a rheostat, and rheostat is not really sensitive to the change in temperature, so we can strike out A and B. And for component Y, it is a thermistor, so when temperature increases for a thermistor, the resistance will decrease. We look at option D. The fan is connected in parallel to the thermistor, so the current that is passing through the fan is equal to the voltage across the alternating supply divided by the resistance of the fan. So we can see that the current passing through the fan is independent of the thermistor here, so D cannot be the answer. And look at C. The thermistor is connected in series with the fan, so as temperature increases, the resistance of the thermistor will decrease and the total resistance of this series circuit will decrease, and it will cause the current to increase, and this will make the fan go faster. So the answer is C. Okay, we are given the voltage and power rating for each lamp, and altogether we are operating 4 lamps for 5 seconds. So to find the energy supplied to one lamp in 5 seconds, we can use the formula. Energy is equal to power times time. So the power is 3 and the time is 5. So each lamp is going to take up 15 joules of energy. And since we have 4 lamps, it will be 15 times 4. This will give us 60 joules of energy. Answer D. Okay, in this question, we are asked why is it safer to fit the switch outside the bathroom compared to fitting it inside the bathroom. Okay, we know that one of the hazards of electricity is damp conditions, and damp conditions will decrease the resistance of dry skin, causing a large current to flow through the body, hence causing electric shock. So by placing the switch outside the bathroom, it minimizes the possibility of water coming in contact with the switch, so this will protect the user. Hence the answer should be B. Okay, we have a compass that is placed beside wire here. So the compass is pointing upwards, so it must have been pointing in the direction of the circular magnetic field that is caused by the current flowing in wire X. So in this case, we can see that the circular magnetic field that is caused by the current in wire X must be flowing in an anti-clockwise direction. So for the field to go in anti-clockwise direction, using our right hand grip rule, the current must be flowing out of the paper. So it can be represented with a dot. Okay, so now let's look at wire Y. The circular magnetic field is also going in an anti-clockwise direction. So using the right hand grip rule, the current in wire Y is also flowing out of the paper, represented by a dot. So with this, right, we can say that the direction of the current, they are the same. And since we have a compass that is placed right in between the two wires and it is being affected by what the current in wire X, we can conclude that the current flowing in wire X is larger than that in wire Y. So the answer is A. Okay, we have a current that is flowing upwards from R to P. So let us indicate it with an arrow here. And the magnetic field is moving to the right from S to Q. So the wire is going to experience a force, and the direction of the force can be found through Fleming's left hand rule. Okay, so the index finger, it represents the magnetic field, and the current is moving upwards, so the middle finger will point upwards, and the thumb is pointing into the paper. So that means this wire here is going to experience a force that is going into the paper, and this will cause the coil to turn about the axis of PR. So the answer should be C.